So we're going to take a look at another type of kind of special system that we run into. And this one's called a partially decoupled system. Now, as you might imagine, partially decoupled means that some of it is and some of it isn't. Specifically, a partially decoupled system is one where one differential equation is decoupled, but the other one isn't. So what does that look like? Well, we've actually seen what it kind of looks like at the beginning of this section. If you remember, at the beginning of the section we said, hey, wouldn't it be nice to be able to solve this system? Well, sort of. We have a similar situation here. Notice that the dx dt is in terms of both x and y. So we could write this as a function of x and y. But the dy dt is actually just a function of y. That's just g of y. So there's our decoupled part. So the partially decoupled part, that's this part of the system right there. And you'll notice we're given initial conditions right here. And the initial conditions are going to allow us to turn our general solution into a particular solution. So our ICs allow us to find a particular solution from the general solution. Okay, so once we have the particular solution, or excuse me, once we have the general solution, we can use those to find the particular. So we're going to do kind of what we did before. We're going to say I'm going to ignore the undecoupled one or the coupled one, and I'm just going to stick with this guy right here. And so we're going to start with the decoupled equation. Because we can say confidently that y, dy dt, does not depend on anything other than the y component. So we can say dy dt equals negative 4y. That thing is going to have a solution that we've seen before. We've run into it before, and it's just y of t equals some constant, we'll call it c, times e to the negative 4t. Right? And if you're feeling woozy about that, you're like, I don't know, I need to be able to see where that comes from. We got that by using separation of variables. So not terribly tricky. You can get from here to here using separation of variables. But here's the good news. That means that whenever I have a y of t, or just a y, I can actually substitute this in, because I know that y equals this in this system of equations. So now when I take a look at my second equation, I can sub that y value, or that y, into dx dt, into the other coupled equation. And so that means I can say dx dt equals, and so I'm just going to grab it from up here, 2x plus 3 times y, which we already know is c1 e to the negative 4t. Sneaky, huh? And so now when I manipulate this thing, I should be able to solve this equation, and let's verify how that works. So I'm going to move my x's to the other side, and we have dx dt minus 2x equals 3 times some constant c1 e to the minus 4t. And if you're looking at this and thinking, that kind of looks familiar, all my x terms are on one side, hey, that's a non-homogeneous differential equation. I can solve that using either the lucky guess method from section 1.8 or the integrating factor method from 1.9. And I know, you all want to use the lucky guess method, but no, I'm going to have us use the integrating factor method. So I can solve this using the integrating factor method. So using the integrating factor method, remember I have to figure out what's my integrating factor, what's my mu of t in this case. It's going to be, well, the -2. It's this constant that's sitting in front of the x, or the function that's sitting in front of the x, and that's going to be e to the integral of -2 dt, also known as e to the -2t. So that's my integrating factor, and that's what I'm going to multiply the entire equation, not just the left side, the entire equation by. And so if I do this right, on the left-hand side, I'll be left with the integrating factor, e to the -2t, times the x, what's right here, so times x. So in integrating factor, e to the -2t, I don't know why I was writing it like this, times the entire equation, which is dx dt minus 2x equals 3c1 e to the -4t. And when I multiply that through, I'll drop the blue marker now, you'll see that I have e to the -2t times dx dt minus 2e to the -2t times x. The other side, I'm still multiplying through by that e to the -2t. I get 3c1 e to the -6t. And now if I played my cards right and I did my integrating factor method correctly, this thing right here, all of this, both of these two terms, it's really the product rule derivative of, with respect to t, of my integrating factor, e to the -2t, times x. And so just pause for a second and verify, make sure that we did it right. The derivative of the first factor would be -2 e to the -2t times x. That's this term right here. And the other term would be this times the derivative of x, so dx dt. Sure enough, there it is. So it worked out. The right-hand side is just what it is. And now I can integrate both sides with respect to t. And when I do that using the integrating factor method, this side just kind of, the integral and the derivative sort of undo each other, and I'm left with e to the -2t times x. I'm going to move the constants due to integration over here and group them together. And so we'll call this, this side will be the integral of 3c1 e to the -6t, which it's not too terribly difficult. We just have to integrate this side, e to the -2t times x. Over here, the 3 and the c kind of come out front. And we have, when we integrate this thing, it's going to be -1/6 e to the -6t. And all of that gets plus another constant. So I'm going to call it plus c for right now. I'm going to call it c2 in a second once we kind of manipulate some things. Oh, no, actually, I'm going to call it c2 right now. We're done. The very last thing is going to be getting x by itself by multiplying by e to the +2t on both sides. And so what we wind up with after a little bit of simplification is an x of t equals the 3 and the 6 on the bottom. That gives us a -1/2 overall. So this is just -1/2 c1 e to the, when I multiply through by the positive, this becomes -4t plus c2 times e to the 2t. And so there's my c1 and my c2, two different constants. So if that's x of t, and you remember from up above that y of t is equal to just plain old c1 e to the -4t. This then becomes my system's general solution. And of course, we're not done because we were told that there's an initial condition. And so we can use our initial condition with our general solution and try to figure it out, or figure out our particular solution. So let's use the initial condition. And if you remember, the initial condition is when t equals 0, x equals 0, and y equals 1, right? And that's our t, our x, and our y. And so the good news is that we can kind of grab this and plug in 0 for t, and in both cases e to the 0 is just 1. Same thing down here. So we really have a set of equations, if you want to think of it this way. And the set of equations is x of t would be equal to 0, y of t would be equal to 1. So 0 and 1. And then the right-hand side for this one would be negative 1/2 c1 plus c2. And then the right-hand side for this equation is just c1. So right away we can tell that c1 equals 1. And if c1 is 1, then this is minus 1/2 plus something equals 0. So that means c2 must be equal to 1/2. So c1 equals minus 1/2 and c2 equals positive 1/2. And that's solving for our kind of our constants for our particular solution. So at the very end, after all is said and done, the particular solution, there we go, solution is, and we can write this as in parametric form, x of t comma y of t. That's going to be equal to negative 1/2 c1, and c1 is 1/2, so that would be negative 1/4 e to the minus 4t plus 1/2 e to the 2t. I'm just getting that from my x of t equation right here. All right, so that's my x of t, comma, my y of t is just c1 e to the minus 4t. So that would be negative 1/2 e to the minus 4t. So that's my particular solution, both the x of t and the y of t. So we should be able to check it and make sure that we did it right. That's always the fun part. So in Maple, we can type our differential equations. Because they're a system, we have to put them together. So differential equation, x of t comma t equals, let's see, what was the first equation? 2 times x of t plus 3 times y of t. And our second equation was dy dt equals just plain old negative 4 times y of t. Now, if we want the general solution, to check our general solution, we can do it this way and just hit enter. And so sure enough, we have negative 1/2 times a constant e to the negative 4t plus another constant times e to the 2t. And the y of t equation is that first constant. Here it's called c2, but yeah, it looks like our general solution is correct. So our particular solution should totally be correct as well. So let's double check. So I'm just going to copy and paste, and in order to get the particular solution, you don't have to add any more brackets. Just within that same bracket, you can type in your initial condition. So x of 0 was equal to 0, yeah, 0, and y of 0 was equal to 1. So I should be able to just hit enter and verify my solution. Now pause for a second and take a look. That doesn't look like my solution. What happened? We had the same general solution. That was correct. But this is not the same particular solution. So instantly that should tell you where we must have screwed up, where the mistake should have been, or where the mistake is. So let's go back and take a look at our notes. We know that we had the correct general solution, but this isn't the same. This isn't correct. So something must have gone wrong between here and here. And so let's double check. Our initial conditions, that was correct. These equations, that's correct. But notice what I did here. For some inexplicable reason, and you probably caught it while I was doing it, I wrote c1 equals negative 1/2. I have no idea why. But c1 doesn't equal negative 1/2. c1 just equals 1. So that's a big mistake. And of course, it doesn't change the general solution. It only changed the particular solution. So c1 equals 1, and c2, if that's 1, then c2 would have to equal negative 1/2. Right? And Maple says the constant over here would be positive 1/2. What am I doing wrong here? Or is it labeled backwards here? It's the arithmetic that gets in my way. So if C1 equals 1, then that means C2 is going to wind up equaling positive 1/2. Okay, so we're right about that one. Whew. So what else do we have to change? Well, this is no longer negative 1/4. And that's not, or that is negative 1/2. No, that's positive 1/2. C2 is positive 1/2. Boop. So this thing sitting in front of my first term on my particular solution, the x of t, is just going to be negative 1/2 times C1, which is negative 1/2 right here. And then positive 1/2 for that one right there. So negative 1/2 e to the negative 4t plus 1/2 e to the 2t. And then my y of t is 1/2 e to the negative 4t. And sure enough, that's not what we have. What did I do wrong? Oh, because that's no longer. Oh, man, I'm just full of it today. See, mistakes happen, but you can catch it. This is no longer 1/2. That's just 1. Boy, you guys are probably having a field day watching this. Right? So the good news for us is we can solve a decoupled system like this by kind of working our way in, paying attention to the part that's decoupled, and then using that to our advantage. This was the sneaky part right here, and saying, hey, I know what y equals because I solved it already, and use that, and then it becomes an integrating factor, or lucky guess, problem, whichever one you want to use. So you have seen an example of how this works. So now the test is, can you replicate this? Can you use this method to find a solution? So I've given you, on the next page, I've given you 2 problems to try. You'll notice these are problems from the textbook. So you can get to those on page 194, number 1, and number 7 on page 195. And I'll tell you that the first one is a fully decoupled system, so that should be good practice for you. The second one is the partially decoupled system. So you've got a fully decoupled and a partially decoupled. To try it out, I will post a scan of this page with my working it out on the course website, so you can get access to that and check your work. But take a second and give this a try. Prove that you know how to solve both a decoupled and a partially decoupled system, and then of course check it on Maple and check it with the posted notes. Okay, that's it for section 2.4. We've got one more section in chapter 2, which is all about using Euler's method for a system of differential equations. So come back for that.